feel we last left off doing, we did the plus minus zero test level problem. Okay. Did we do much past that? Okay. Oh, that's right. You were just craving math, more math. Let's do it. Let's start out with velocity. Average velocity. All right, average velocity is, I can write it two other different ways. This tends to be the way I'll write it. Sometimes I'll drop the G. But just in case, for whatever reason, I do it slightly differently. I can also write it like this. And I can also write it like this, with a bar over it. This looks too much like my vector symbol, so I tend not to. This shows up, this is actually what's referred to as the expected value, which for what we're doing is just the average. But we're talking about the average velocity and just two other ways that I might write it. And that's just going to be equal to displacement divided by time. Now I said just displacement, I got a triangle right there. Really that's change in position, which is the same thing as displacement. If you're ever given a question of what was the change in position and then later what is the displacement, it's the same answer. Despite what some students have tried to tell me on tests. All right, so let's go with a one-dimensional problem right now. Yep. One-dimensional problem, I've got a, let's say I'm right here. We'll make to the right positive. And I go from 1 meter to 7 meters in 5 seconds. So I got things marked out on the floor. I'm standing, I start out at the 1 meter from on the positive side of 0. So 0 would be behind me. And I walk to 7 meters in 5 seconds. So, average velocity. Well, what's my change in position?
6 meters.
Positive or negative?
Positive.
Absolutely. It's final minus initial, so 7 minus 1. So this would be 7 minus 1 divided by the amount of time it took. So it's 6 over 5, or 1.2 for meters per second. It's not claiming that the velocity is constant during that time, it's just that that's the average. Matter of fact, I've seen it in various rural parts, speed checked by aircraft. Have any of you run across that? Maybe they don't do it anymore.
Is that say 1D? What does that say?
1D is one-dimensional. There used to be, or places that you've never been, speed check by aircraft. What they're doing is that there's two landmarks that they're looking at, and they basically time how long it takes you to get from one to the other, and they know the distance, they divide by how much time it took, and they know what your average speed was, and if it's above, then they presumably either send you something in the mail or probably at that time call somebody down on the ground to come pull you over. Or maybe it was a fake threat. I don't know if anyone's actually gotten pulled over by that, but I've seen the signs. Now, it just so happens that, say I'm plotting that. So I start out at, so this would be time. So it's 0 seconds, 1, 2, 3, 4, 5. And then this will be position. And I go from 1, 2, 3, 4, 5, 6, 7 meters, 10 seconds. I don't know based upon this small little bit of information, if I know I start at 1, and after 5 seconds, I'm at 7, which hopefully is somewhere around there. I don't know if it's a straight line, or if it's curved, or, I do some sort of funky maneuver. I just know after 5 seconds, I've gone 7 meters. If the velocity is constant, then it's just a straight line. If I'm speeding up, then it's curved like that. If I'm slowing down, it's going like that. So average, we really don't know what happens in between. However, if we're dealing with a constant acceleration, well, actually, before we get there, let's just start off and assume we have acceleration of 0. If acceleration is equal to 0, my graph is going to be a straight line like that. Now, if you think back to if you're doing the linear motion lab, the one where the last page is like 17 questions of, okay, that reference won't mean anything to you then. It just so happens, if you think about this, average velocity is change in position over change in time. If I have a position time graph, there's my change in position, there's my change in time. What is change in position over change in time, besides average velocity? Think math class. What'd you say? No, not the hypotenuse.
It's slope.
Yes, that's the rise, that's the run. So my velocity versus time graph is the slope of my position versus time graph. So if my slope is constant, of my position time graph is constant, then my velocity is constant. In a similar way, acceleration, technically average acceleration, is the change in velocity over the change in time. So that's just a rise over run of my velocity time graph. If I have velocity inverse time, if that's my graph there, this is my rise, change in velocity, this is my run, change in time. So acceleration versus time is the slope of velocity versus time. As a side note, anyone in here had calculus? Occasionally I get a 110 student who's had calculus, not regularly. You've had some? Okay. Derivatives. This is the derivative of that. This is the derivative of that, or the second derivative of this. I don't know if the words.
It's been
Right.
3 years.
Okay.
Yeah.
At some point, the memories come flooding back, and you'll just get this feeling of overwhelming joy. So in this particular case, if my position versus time graph is a straight line, slope is constant, my velocity time graph would look like that. Slope is constant, so my velocity is constant. What's the slope of this line?
0.
Yeah. The horizontal lines, slope is 0. So my acceleration time graph would just be 0. So if acceleration is 0, this is a line at some angle, this is a flat line, and that is just on 0. Excuse me. If acceleration is not 0 though, let's still assume it's constant. A constant acceleration So let's sort of work backwards. If acceleration versus time is a constant, let's assume positive. This is the slope of my velocity time graph. So if acceleration is constant, that means the slope of my velocity time graph is also constant. This is positive, so my velocity time graph will be a positive constant. So my velocity time graph, the slope, it's positive and constant. Positive slopes, negative slopes. And so this means I'm starting out slowly and I pick up speed as I go, so I'm going to be, so the farther along I am in time, I'm covering more ground in the same amount of time. So, 1 second here, I might travel 2 feet. Here, I might be traveling 6 feet. I'm traveling more distance in the same amount of time as we progress. And so my position time graph, well, it starts out slowly and then gets steeper as we go. Which also leads into, I think most of you have dealt with finding the slope of a straight line, but how do you find the slope of a curve? What would you do if this were position versus time? What's going on here?
There's multiple slopes.
Indeed, there are. So how do you find the slope at, say, this point?
I know it's positive.
Yes, and as far as 110 goes, that's a key thing I want you to pull out of that. What about the slope there versus the slope there? Which one has the greater slope?
The highest peak.
Which one?
Whichever one has the highest peak.
If we call that A and that B, which one has the higher slope?
B.
Because it's farther up? Is that the thinking?
Yes.
Okay. You're not sure about why you're thinking that? This feels right?
Yeah, this feels right.
Okay, there we go. Anyone with a different opinion, or we're just saying Priscilla said it, so it's gotta be true?
I'm just trying to think. I don't know, wouldn't it be this?
I thought it would be the highest peak.
Wouldn't
Or
it?
the highest point.
If this were a velocity time graph, it would be, but it's a position time graph, it's a little bit different.
I think it might be A,
Why A?
because it looks steeper.
All right. Imagine this were a mountain and you're walking down it. Would you have more trouble here or here?
At A.
A.
Yeah, it's steeper. A has a bigger slope to it, you're traveling faster at this point. Now, the way that they do it in math class, we're not gonna go into, I'll give you the concept of it, not going into the actual how to do a derivative, unless you want to. I got one head shaking no, got a couple head shaking no, and a lot of other people just staring at me. Okay. The way you do it in math class is you draw a tangent line at that point. Tangent line is a line that just skirts at that point and doesn't officially cross them. So at this point right here, you would draw a line that just skirts at that point right there. It should be a straight line, so presumably in your notes it'll be better than that. And what they actually do is find the slope of that line right there, of that tangent line. So here, do it here, it's gonna be easier for me. You draw a tangent line at the point in question and you find the slope of that line, and so that's how you sort of know what the slope is. So at A, my slope is like this, but the line is like that. At B, it is not as steep. What's happening here?
Is the slope starting to turn?
Okay. Which means what?
It's going from a positive to a negative.
Okay. Keep on.
That's where I'm lost.
Okay. We are indeed going from a positive slope to a negative slope. But what is happening, in order to go from a positive slope to a negative slope, what's going on?
Zero.
The position is changing.
Say it again?
The position is changing.
One more time.
The position is changing.
At the position, well, position changes actually everywhere except there.
So it's staying constant.
So you
Very
can do-
briefly, at this point right here, remember that the slope is velocity versus time. We go from a positive velocity to a negative velocity. And if you go from positive velocity to negative velocity, what do you have to pass through?
Zero.
That's where the velocity is zero. This is the turnaround point. So you're moving farther and farther away from the origin, and then this is the point where you stop briefly before you start heading back towards it. And then you stop again here. From a math point of view, from a slope point of view, the tangent line at a peak or the trough should be a flat line, drawn better than that. Should be a flat line that just skirts it at the top. Slope of a flat line like that is 0. Now know what you're thinking. Hey, all this is great, but it still sounds conceptual. Where are the numbers? All right, here's one. If my velocity, let's go back to the simpler example of, I have a constantly increasing velocity, in other words, I have a constant acceleration, constant positive acceleration here. And I'm trying to find the average. Yeah, I could find the average if I knew what the position was at this time and the position at this time. I could find the change in position over change in time, plug into my formula over there, great. But what's going on here? Well, let's take a look. So let's give a number here. Let's say that this represents 6 meters per second squared. What acceleration means, change in velocity over change in time, this means that the velocity is going to change by positive 6 meters per second every second. I could write that as 6 meters per second per second. That means the same thing as meters per second squared. Now, as a final answer on a test or quiz, that's not really appropriate because I got 2 fraction guards there for the units. But meters per second is what's going on when you're dealing with acceleration. So if I start out, so at time, we'll do our acceleration is 6 meters per second squared. Positive, time is 0. The initial velocity is, when we say it starts out at 10 meters per second, and then 1, 2, let's find out what happens after, let's go to 8 seconds. So if it changes by 6 meters per second every second, what's the velocity after 1 second?
6. Or
16. It changes by 6 each second, instead of having to write the units over and over again. After 2 seconds, you're spellbound. Really. What did you say?
22.
Yes. How'd you get that?
I added 6.
Yeah. After 3 seconds,
28.
you gonna let Yvette do this all by herself? Keep believing you.
34.
Or 2.
32.
No.
Is that 32?
You were right, 34, don't mind.
40. 46. 52.
Or 52, that time, that was on you.
I said 52.
Oh, sorry, I misheard, that was on me then.
58.
58, all right. Now we can check to see if our acceleration matches what we have here. Do we make a mistake or not, as I would have apparently. My average velocity, well, if it's constant, my average is the same as my instantaneous. It's the same either way. So I've got my change in velocity, so it's 58 minus 10, divided by the amount of time, 8. So that's 48 divided by 8, which is 6. That would be my acceleration based upon the numbers I have written there. That worked out. Average velocity. How would you find the average velocity? Because we don't have, we can't find average velocity this way, or not easily. How do you average numbers?
Add and divide.
Yeah, so it's helpful if more than one person does this. What's the average of those? Now, some people might see a shortcut already. There are a couple of shortcuts, but. You add them all up and divide by 8? How many numbers are there?
No,
8.
34.
There are 9 numbers. Now, one of the common mistakes is you forget about 0. You look at the time, but don't forget this is one of the numbers you added in there. So there are actually 9 times here. So divide by 9 and you end up with, as you said, 34. So my average velocity is 34 meters per second, so that's my average. If I want to figure out how far I traveled in that time, well, then I can use this up here. That's going to be how far I traveled. It'll be my displacement, and since I'm only traveling in one direction, it'll also, the magnitude will be my distance. So let's check that out. So I know my average is 34. That's going to be equal to my displacement divided by time, which was 8 seconds. So my average, my displacement is just 34 times 8. 272.
Not 34 times 9?
No, because the time
Okay.
is 8 seconds still.
Okay.
And I assume that number's right. Looking for some sort of nod of acceptance or someone to say, who raised you?
That's right.
Okay. Units?
What is it, meters? Okay.
Yeah, what is the displacement? Say it with great confidence.
Meters.
Great confidence.
Meters.
It is meters. So you're going to travel 272 meters.